In this exercise here, we have to answer two questions. The first question is, for which value of alpha, we're told that there's only one value, but we'll see that. For which value of alpha, this integral is a convergent integral. And the second question is to calculate the integral for that value of alpha. Well, because of the second one, we could directly calculate primitives of this, because it is, well, presumably you can calculate the primitive of this integral here, or this function here. Otherwise you couldn't compute this integral. However, suppose that the only question that you want to answer is this one, and you don't really want to calculate the integral, or for some reason you can't calculate the integral. So you have to figure out a method to assess whether this integral is convergent or not, or for which values of alpha it is convergent, right? So we need to find what is the behavior of this whole function when x is very large. We have a problem here because when x is very large, this goes to 0 and this also goes to 0, right? But they somehow compensate each other in a way that, well, how they go to 0, because this one goes to 0 as 1 over x, and so does this one as 1 over x. How does this go to 0? It's important, right? Because the faster it goes, the more chances are that this integral converges, right? Actually, we have already guessed a bit what this is about, because the behavior of this function is when x goes to infinity is as 1 over x, because the 1, for x very large, the 1 doesn't matter. So you have here the square root of x squared, which is x. So this behaves as that, but the primitive of this, or the integral from 0 to infinity of this, is divergent, right? However, this one behaves similarly. So alpha over x plus 1, because x is large and 1 is a constant. When x goes to infinity, this goes as alpha over x when x goes to infinity here. So you have something, or two, if you separate these into two integrals, both of them diverge. But actually you don't have to, because what you have is a single function here in which these two terms can cancel. Actually, well, you can see that if alpha is equal to 1, then this term here behaves exactly as this term here, and the leading term cancels. So the hope is that the rest of the term are convergent. Well, we'll refine this argument a little bit. And for that, what we have to do is to expand this in Taylor. Well, we can do just a Taylor expansion like that, because we are expanding around x going to infinity. But what we can do is to, well, let's say, transform this x to infinity into another variable going to 0, for instance, t, right? So x to infinity becomes t going to 0 plus, right? And then if we make this substitution here, what we have is that 1 over square root of 1 plus x squared is 1 over square root of 1 plus 1 over t squared. And if we multiply, then we end up with this other function, right? And similarly for this one, right? If we write it in terms of 1 over t, what we have is 1 over t plus 1, which is t over 1 plus t. All right, now we can expand this more easily. So what we have here, remember this, the denominator here is of the form 1 plus u minus 1/2, right? And if you remember the expansion of the binomial, when u goes to 0, it is 1 minus 1/2 times u. So the exponent times this plus ou when u goes to 0, right? So we can use this here. Then we have t times 1 minus 1/2 t squared plus ot squared, right? Which is t minus t cubed half plus ot cubed when t goes to 0, right? And here, well, we have 1 over 1 plus t. This is, we can apply, well, actually this is 1 minus 1 over 1 minus t, which is, we can apply the geometric series expansion, and then we have t times 1 minus t plus t squared plus ot squared, right? You can stop there, because then we have t minus t squared plus t cubed plus ot cubed when t goes to infinity, right? And now we can just subtract, okay? If we subtract both functions, both these functions, in terms of t, what we have is, this first function is t minus t cubed half plus ot cubed, and we have to subtract alpha times this other function, right? So minus alpha t plus alpha t squared minus alpha t cubed plus ot cubed. All right, and then, well, you have here 1 minus alpha t, right? And then you have plus alpha t squared, and we can stop there because all the rest of the powers are higher than the second, right? Or even negligible with respect to the third, so the rest is ot squared. So we can just ignore the rest when t goes to 0. Okay, in terms of the all x variable, this would mean that 1 over the square root of 1 plus x squared minus alpha over x plus 1 is just 1 minus alpha, it would be 1 minus alpha divided by x, because t is 1 over x, plus alpha divided by x squared plus o 1 over x squared when x goes to infinity. Okay, so now we have everything that we need, because if alpha is different from 1, the leading term is this, and the integral of 1 over x from 0 to infinity, well, actually it's not from 0, is it? Oh yeah, it's from 0, but okay, but at 0 this integral is not singular, right? So all that matters is what happens at infinity. So we can just study what happens with this integral. Sorry. From, let's say, from 1, right? Well, you can do as we do several times. You can separate this integral into the integral from 0 to 1, which is a normal ordinary Riemann integral, and then from 1 to infinity. This one is the one that we have to analyze, so it's this one we should be worried about. This diverges, as I said, because the exponent here is 1. So the only, and that happens if alpha is different from 1. So the only possibility, as we have guessed at the beginning, is that alpha is equal to 1 for this to converge. And when alpha is equal to 1, this term cancels. And what we have is that the leading term is 1 over x squared. And the integral of 1 over x squared, this is a finite integral. So the answer to the first question is alpha is equal to 1, right? Okay, as I said, in this particular case, there's no need to do this, because in order to answer the second question, we need to calculate the primitive of this function. And if we are able to calculate the primitive of this function, we can just answer to the first question taking a limit, right? So now that we know that alpha is equal to 1, let's try to compute this integral here. So we have the integral from 0 to, let's say, u, right? So u is any number, any positive number, okay? Then we'll take the limit u to infinity, right? And what we have here is 1 over the square root of 1 plus x squared minus 1 over 1 plus x. Okay, this is a convergent integral, right? We know that. And we just have to calculate it. But the second integral is straightforward. It's just the minus that is here, the logarithm of 1 plus x. Well, in principle, you have to put an absolute value here, but x is always positive, so we don't have to. And the limits are 0 to u, right? And then you have the second one, which is the integral from 0 to u of dx over square root of 1 plus x squared. How do we do this integral here? Well, one way, this integral here is, by the way, when x is equal to 0, this is the logarithm of 1, which is 0. And then you have just minus the logarithm of 1 plus u. Okay, so this integral here just produces that. And in order to do this second integral, this integral here, what we're going to do is to make a change of variable. We're going to introduce the variable x equal tangent of y, right? Because then what we have here is, in the denominator is 1 plus the tangent square of y, which is the second square of y, or 1 over the cosine squared, as you prefer, right? So, and dx, of course, is dt is the second square, the derivative of the tangent, which is the second square, dy. All right? So we substitute there, and we have, when x is equal to 0, the tangent, well, the angle for which the tangent is 0, so this limit is easy. The limit here is the angle for which the tangent is equal to u. So it's the arc tangent of u. That's the upper limit, right? And then we have the second in the denominators with a square root, so it's just the second of y. And up here we have the second square, dy. So we have minus the logarithm of 1 plus u plus the integral from 0 to the arc tangent of u. And we have to integrate is the second of x. Second of x. Dx, right? Well, remember the integral of the second is the logarithm of the second plus the tangent, all right? By the way, well, I'm using all the time y, so let's keep it to y. It doesn't matter much because we're integrating over this variable, but just to avoid confusion, this is y, this is y. So that must be y2. Must be y here and y here. So second of y, tangent of y, right? Plus a constant, but the constant is irrelevant because we can take whichever primitive we like. So we're going to get rid of this constant. We don't need it. All right. On the other hand, the angle here is positive, and both the second and the tangent will be positive. So actually, we don't need the absolute value. We can get rid of the absolute value and just write this, the logarithm of that. Okay, so what we have here is minus the logarithm of 1 plus u plus the logarithm of the second of y plus the tangent of y. Okay, the tangent of y is just x, so we can just write here x. The second of y, well, we can infer it from here, is the square root, second of y is the square root of this, and since this is x, the tangent is x, so this is just the square root of 1 plus x squared. Okay, and we have to substitute x between 0 and the arctangent of u. All right, no, sorry, if we recover the original variable, we don't have to do that. I'm sorry. If we recover the original value, variable, this is just u. All right, this is just u. Okay, so this is minus the logarithm of 1 plus u plus, and here we have for 0, this is 0, and this is 1, the logarithm of 1 is 0, so it's the logarithm of x, u, plus the square root of 1 plus u squared. Okay, so this is what we have. We have, as a result of this integration, we have the logarithm of u plus the square root of 1 plus u squared over 1 plus u. All right. So what we should do now is to calculate what is the limit of this, the limit of that function, the logarithm of u plus the square root of 1 plus u squared over 1 plus u, right? When u goes to infinity. And that is the answer to our integral. Okay, that's the value of our integral. All right, so we have to calculate the limit of this and then calculate the logarithm. So what is the limit of this? Well, the leading term here is u. The leading term up here is u from this bit, and here, if you factor out the u squared, is also u. So you have u plus u is 2u, and down here you have 1u, so the limit is the logarithm of 2, 2 divided by 1. So that's the value of the integral, the logarithm of 2, for alpha equal to 1. For alpha other than 1, the integral is divergent.